Good day, students. I believe you all have been doing well. My name is Mr. Emmanuel, and in today's physics class, we'll be learning about the topic equilibrium of forces. At the end of the topic, you will learn what equilibrium is. You'll learn the difference between equilibriant forces and resultant forces. You be able to, you should state the conditions necessary for equilibrium, understand what moment is, coupled, and how these are applied, real life application of these concepts. And also at the end, you'll be able to solve numerical problems that involves equilibrium of forces. So we'll begin shortly. Get your writing pad, your pen, your calculator, and most importantly, your listening ears. Participate in every activities that we'll be doing and think alongside with me. And we'll go, thank you very much. We'll go into the main lesson. Equilibrium of forces. Equilibrium of forces. So we will start by defining what equilibrium is. And English, from English perspective, equilibrium is a state of balance, a state of equality. Yeah, from the English perspective. It means when we're talking about equilibrium of forces, we're talking about the when forces act, the total force or net force or the resultant force acting on a particular body is such that the net effect is zero, meaning the total force acting on that body has a net force of zero. And when this happens, the body moves with a constant acceleration, with a zero acceleration. And by zero acceleration, mean there is no acceleration, mean the object is moving with a constant velocity. Okay, let's get to the physics aspect of it. So equilibrium is a condition in which the resultant or net force acting on a body are equal to zero. So equilibrium is a condition in which the resultant force, the resultant or net force acting on a body is equal to zero. Yeah. Okay, let me explain this with the aid of a diagram. Let's see a box on an horizontal floor. Let's say this is my horizontal floor. Is acted upon by two forces in opposite direction. Parallel forces in opposite direction. Let's say the force here is 100 Newton and the force here is 100 Newton. From what we've done under vectors, the resultant or net force here. So the resultant force here is 100 minus 100, which is 0 Newton. So in other words, this box is in a state of equilibrium because the net force or the resultant force acting on the box is equals to 0. And as a result of that, the box does not move because it has no acceleration. And when there's no acceleration, it means the velocity is constant. Why do I say so? Let's go back to the equation for calculating acceleration. We know that acceleration is the rate of change of velocity with respect to time. So this is acceleration. So when the velocity is constant, it means both the initial velocity and the final velocity are equal. And when we do that, so let's say both of them are equals to let me say x. So I have a equals to x minus x over t, which is giving me 0 over t, making the acceleration 0. Meaning a body that is in a state of equilibrium is either moving at a constant velocity or at rest. I believe this is well understood. Let's get to define some things as it relates to equilibrium. So we'll be looking at two types of equilibrium. And before that, remember from our laws of motion, that's the previous topic we treated in class. The second law of motion tells us that the force, which is the net force, is directly proportional to the mass and the acceleration, where we have constant to be equals to 1. So we have that the net force is equals to ma. Now, what the second law tries to explain is that when the net force on an object is what actually gives the object an acceleration. And if the net force is 0, it means the acceleration is 0. For example, let's look at another, let me draw another instance of this box. Let's say 50 Newton is acting on it rightward and 30 Newton is acting on it. Our net force, which is the resultant force, it will be equal to 50 minus 30, which is 20 Newton. And according to the Newton's second law, this force, this is what gives the object an acceleration. So, and we can, if the object moves with a particular acceleration, let's say 2 meters per second squared, we know that let's say the object, so let's say the object has a mass of, let's say, 4 kg. It means the object will move at 4 times. So the acceleration that the object will move with is 5 meters per second squared. It means in the direction of the 15 Newton. So the object will move. So the resultant force is in this direction with an acceleration of 5 meters per second squared. So this is Newton's second law of motion, and that is what it's given to us. And let's consider some of the types of equilibrium we have. So let's look at the types of equilibrium. So we'll consider two main types of equilibrium: the static equilibrium and the dynamic equilibrium. So for the static equilibrium, we have, so let's look at it, the static equilibrium. Static equilibrium is a condition of a body at rest where the resultant is 0. That is all about the static equilibrium. For static means stationary, not moving. So for static equilibrium, we have that the body is at rest such that its acceleration is 0. Okay, let's look at that. Static equilibrium. So for the static equilibrium, we have that it is a condition of a body, at rest with the resultant force equal to 0. So this is the keyword, with the resultant force equals to 0. Aside that, we have the dynamic equilibrium. So for the dynamic equilibrium, is the condition of a body that is moving with a constant linear velocity or rotational speed with the resultant force on it equals to 0. So the keyword for static equilibrium, the keyword is that the body is at rest, and because the resultant forces acting on it are equal to 0. And for the dynamic equilibrium, the keyword is that the body is moving with a constant linear velocity or a rotational speed if it's a body that is rotating, and with the such that the resultant on it is equals to 0. Very, very important. So these are the two types of equilibrium we have. So what are the conditions for equilibrium? So we're going to state conditions for equilibrium. So conditions for equilibrium. So a body is said to be in equilibrium when the body as a whole, number one. So when the body as a whole either remains at rest or moves in a straight line. So either the body as a whole, the body as a whole either remains at rest or moves in a straight line, almost in a straight line with constant speed, And second condition for equilibrium is such that the body is either not rotating, the body is either not rotating or it's not rotating at all, or it is rotating at a constant angular velocity. So the first one talks about linear equilibrium. And then the second one talks about rotational equilibrium for body that are rotating. So these are the two conditions that are very important for us to know. So the first one, which is linear equilibrium, tells us that the body must either be at rest, and if it is not at rest, it is moving with a constant speed, meaning the acceleration is zero in a straight line. Then for the rotational equilibrium, we mean that the body is either not rotating at all, or when rotating, it must be rotating with a constant angular velocity. And very, very important. So you must take note of these conditions. Very, very important conditions. So let's look at, we'll look at equilibrium of parallel forces. Equilibrium of parallel forces. The equilibrium of parallel forces. So for parallel forces, we have that the sum of forces or moment is zero. So sum of forces or moments is zero. And the other condition is that let me explain this. Sum of forces or moments is zero. By what we mean is that the sum of the upward forces, let me see, the upward forces should be equal to the sum of the downward forces. Very, very important. So let's say if you have an object in equilibrium, if you have two forces, 3 Newton, and let me say 5 Newton, for it to be in equilibrium, you must have a downward force, which is 8 Newton, to keep this body in equilibrium. For let's look at equilibrium of non-parallel forces. So for non-parallel forces, we have that they must be coplanar. They must be coplanar. And by coplanar, we mean that they must not be on the same line. So not on the same line. And that is they are not collinear. So that's what we mean by coplanar. So they must be coplanar, meaning they must not be on the same line or collinear. And they must be concurrent. Two is that they must be concurrent. And what do we mean by concurrent? Meaning they must be passing, we are passing through a common point. So forces like this are concurrent that passing through common points. So these are concurrent forces. So let's see diagram that will explain. Another condition is that they can be represented by a one property that they can be represented by or a polygon. Of forces. Now let's see what in these are these are collinear. These are collinear. These forces are planar. They are not collinear. These forces are concurrent. So what is concurrence? And this, so this is all that have been explained in the diagram. Very, very, very important. We'll get to use this to solve problems. Another important thing we'll need to know before solving problems is we need to differentiate what between resultant forces and equilibriant forces. We need to differentiate between resultant forces and equilibriant forces. So what are these? What are equilibriant forces and what are resultant forces? Now, we'll begin with the resultant force. We'll begin with it. Now, the resultant force is just a single force that will produce the same effect in magnitude and direction as when several forces act together. And I will break this definition down for you to understand. And we'll say the resultant force is that single force that will produce the same effect in magnitude and direction as many forces combined together. Will mean that the resultant force is that force that will give us the same effects as several forces combined together. For example, if I have an object that, let's go back to our box model. If I have these forces acting on this object, let's say 50 Newton and 30 Newton, the resultant force is the net force. The effects of these two forces on that object. And the effect of these two forces on that object is that the object will move in the direction of the force, of the higher force. So that means this box will move in the direction of the 15 Newton with a net force of 50 minus 20. So the net force or the resultant force will be 50 minus 30 Newton. So it means this 20 Newton will produce the same effects in both magnitude and direction as when these forces 30 Newton and 50 Newton are acting together. It's just like saying, instead of me instead of me getting two people to pull this box towards them, or rather just push it with a force of 20 Newton, it will produce the same effect as these two forces. I believe that is well explained. So the resultant force is that single force that acting alone will have the same effects in magnitude and direction as two or more forces acting together. So this is all what I mean by the resultant force. Now um, let's look at the equilibriant force. Equilibriant force. Now the equilibriant force of two, so the equilibriant force of two or more forces is also a single force that will balance all other forces. From the word equilibrium force, balance, equilibrium means a state of balance. So that single force that will balance every other force. So called the equilibrium force. So the equilibrium force is that single force which will balance all the other forces taken together. And one thing you should know is that the equilibrium force is equal in magnitude. But opposites in direction. To our resultant force. Very, very important. Very, very, it is equal in magnitude but opposite in direction to our resultant force. I will explain this with a vector diagram where we have three forces, three concurrent forces. Yeah, so we have three concurrent forces, F1, F2, and F3. So if these three forces are acting on these three points, this is their common points, and they are all in equilibrium. So the resultant of any two of the forces is equal but opposite in direction to the third force. What does that mean? Let's say, let me see. Let's say the resultant of force F1 force F1 and force F2 so the resultant of force F1 and force F2 is equal in magnitude to the third force F2 but opposite in direction. So this is the resultant of the first F1 and F2. So the other force here, so this is the resultant of force F1 and force F2. So the third force, this one here, is the equilibriant force. This is getting interesting, very interesting, right? So let's see, look at let's check another. So let's see the same force again, the same forces that are in equilibrium. So F1, F2, and F3. So let's the resultant of F1 and F3. So let's force F1. Let me say we are dealing with this. Force F1 and F3 now. F1 and F3. F1 and F3. So the resultant of F1 and F3 will be equal in magnitude to F2, but opposite in direction to F2. So this is the resultant. So resultant of F1 and F3. And this is the F2 now becomes the equilibriant force. So, and this one is one that balances the other two forces, F1 and F2, to keep them in a state of equilibrium. I believe this has explained all of this. Very, 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 very important. Very, very important. Very, very important. So we will check out a very, very important concepts that will help us in calculation. We'll look at the triangle of forces. The triangle of forces. So we use the triangle of forces when we are dealing with the equilibrium of three forces acting at the point, the equilibrium of three forces acting at a point. By that we mean the equilibrium of three concurrent forces. That's when we use the triangle of forces. And what does the triangle of forces tell us? It states that if three forces are in equilibrium, they can be represented in magnitude and direction by the three sides of a triangle taken in order. So this is what I will explain. This is very simple. I've noticed over the years that students struggle to apply the triangle of forces in solving problems that relate to equilibrium of three concurrent forces. And this arises based on the fact that there is lack of understanding of what the statement of the triangle of forces is. And I will explain this in a very simple terms for you all to understand. So it says that if we have three forces and these forces are in equilibrium, we can represent them in magnitude and direction just using the three sides of a triangle. By that, and we are taking them in order. I will explain what we mean by taking in order with uh, what we have here. Okay, I'll bring, let's say, um, we have three forces like this. Three forces. Let's use the first one, the first diagram of this one, because there are three forces. So you can see is the one with F1, F2, and F3. So these are the three forces. So according to the triangle of forces, if these three forces are in equilibrium, we can represent them in magnitude and direction by the three sides of a triangle taken in order. So the way we do that, I'll make this colorful so that now let's start with this first force, the F1. The F1. So what we do in this is we are going to draw, look at my gun, a line that will be which represent a side of the triangle, but will be parallel. The line of action is parallel to that. This is my F1. So let me mark it F1. So let's go to the F2. The F2. For F2, let me use a black line to represent. So the F2, I'm also going to draw the line that is parallel to it. I will draw it in such a way that three of them will form a triangle. So for me to have a triangle, I can draw this line to be parallel to that. So let me draw it parallel from this where this one stops. Is it parallel? Then let's go to the third one. Use red. So I'm using red. So it's vertical. Also draw vertical line like this. So you can see the triangle has been formed. This is my F2. This is my F3. So and from the the resultant of F1 and F2 is the line that is equal in magnitude to F3 but in opposite direction to it. Like that. So this is the triangle that has been formed. And it's very. So let's check another one. Let's check it out. Let's say we have three forces like this. Okay. So this is another force here. How do we draw the triangle of forces here? Remember, you draw your lines parallel to each force. This is F1, this is F2, and this is F3. So let me draw my F2. It should be parallel to this one. This is the first. This is my F2. You can see it's parallel. I can draw my F3 from here. to be parallel to that parallel. So let me draw a parallel to it, to F3. Just draw a line. Parallel. So this is my F3. And you can see my F1. I'm drawing parallel also. And where it meets this forms, you have a triangle that will be formed there. This is my F1 there. You can see a triangle has been formed. This is the triangle of forces. Very, very important. And we'll use it to solve a problem here. To solve a problem. Okay. Let's solve an example. Very interesting example. Say two forces, 10 Newton, 10 Newton each are inclined at 120 degrees to each other. Find the single force that will A, replace the given force system. And B, balance the given force system. Okay, so let's solve this problem. So one best strategy is to draw the force diagram of the problem. So we have two forces 10 Newton each are inclined at 120 degrees to each other. So 120 degrees to each other. So this is 120 degrees to each other. Find the single force that will replace the given force system. So before we start solving, let's think, what do we mean by a single force that will replace the given force system? Let's go back to our definition of resultant force and equilibrium force. We say the resultant force is that single force that will produce the same effects both in magnitude and direction as several forces combined together. It means A is telling us to get the resultant force because that is the force that will replace the given force system. Remember, it says it's a single force that will produce the same effect, that means a replacement that will produce the same effect as the other forces acting together. So in other words, the first part of our problem is to get the resultant force. The second, balance the given force system. So I believe somebody is saying, wow, this could balance, the keyword is balance. Yeah, the keyword is replace. So balance, you're talking about the equilibriant force. Good. We've interpreted the question and then we are now well equipped to solve this problem. The next thing is how do we get the resultant force? Remember, these forces are 10 Newton each. Remember, from the topic we did under vectors, we talked about the resultant forces also of a system of vector. And we said we use the parallelogram law. Then we'll have two forces inclined at an angle to each other. Now we can represent them both in magnitude and direction by the sides of the parallelogram. And this is, we can see, we can reproduce this to form a parallelogram. So just draw sides parallel to, you can see a parallelogram has been formed. The resultant is, this is the meeting point. These are concurrent forces. This is the meeting point. The resultant is the diagonal of the diagonal of that. So this is the resultant force. So we can use a parallelogram law to get our resultant force. So here is 10 Newton. From what we did in class, we say it is better to get this angle here, which is 180 minus 120, which is 60 degrees, so that we can apply the cosine rule to solve our problem. So let's use the cosine rule to solve our problem. Using the cosine rule, we have that the square of that resultant here is equal to the sum of the squares of the other two sides minus 2 times the product of those two sides plus the angle opposite the resultant, which is the 60 degree that we calculated. So let's solve this mathematically. This is 100 plus 100 minus 200, because 60 is 0.5. So we have 200 minus 100. So r squared is equals to 100. So r will be the square root of 100, which is what? 10 Newton. So the resultant force is also 10 Newton. Well, we can get the angle is a vector. A vector has both magnitude and direction. So the area is the magnitude of the resultant. So this is the magnitude of the resultant. So we need to get the direction. How do we get the direction? We can redraw this triangle here from that parallelogram. Minor drawing. We have 60 here. We have R. Our R now is 10 Newton. And we have 10 Newton here. We have 10 Newton here. So let's get the angle the resultant made with this 10 Newton. So let's call that theta. Or better still, let's use alpha there. We can use any. So we can apply the sine rule to solve that sine rule. So apply the sine rule. Using the sine rule helps us to solve, to get the side or angle of maybe a scaling triangle or a triangle when we know maybe two sides and an included angle. So let's see, we are looking for, we have to calculate the vector. So we have this and this and this. And see, so we can use these two sides. So according to the sine rule, we take 10 over the sine of the angle opposite to that side is 60. So we have sine 60 is equals to the 10 Newton here and the sine of the angle opposite to it, which is sine alpha. So when we solve, we'll see that sine alpha, let's cross multiply here, 10 times sine 60 over 10. So basically, we still have the same thing. So sine alpha equals to sine 60. So we still have that alpha is still 60. Yeah, that means the resultant is that. So we have that our resultant force is what 10 Newton, but at the direction of 60 degree. So the 10 Newton force. So let's say with each of the forces. So that's the resultant. Now, the second part of the problem is for us to get the equilibriant force. Now, let's look at how do we get the equilibriant force? Remember, the equilibriant force, these are the two forces, 10 Newton, is opposite, is equal in magnitude to the resultant, but opposite in direction. So this is our equilibriant. Yes. So B, our equilibriant, force will be have the magnitude of R still 10 Newton, but the direction will be opposite to the resultant. So direction directed opposites. So R, which is our resultant. Wow. So this is quite, so we've been able to affirm this process. So solving physics problem, you have to have a good understanding of the concept behind that problem. So you analyze, have an understanding, and from the parameters you have, you can solve the problem. So we'll pick another example where we apply the triangle of forces. So we'll apply the triangle of forces. So let's see example 2. Example 2, let's say a mass of 2.0 kg is supported by 2 cords, which make angles of 30 degree and 50 degree with the vertical. With the vertical. With the vertical. Calculate the tension in the 2 cords. Calculate the tension in the 2 cords. Okay, so let's take a look at this problem. So we have a mass of 2 kg is supported by 2 cords which make angles of 30 degree and 50 degree with the vertical. Calculate the tension in the 2 cord. How do we resolve this? Now, the way we do this is, first of all, I advise students to draw the diagram, the first diagram. So I will begin with that. It will make work very easy for you, and I will guide you on how to draw the first diagram. Now we have a mass. Remember, the mass will have a weight definitely because it's on the edge surface. So it is acted upon by gravitational force. So to have a weight, and the weight is the mass times the value of the acceleration due to gravity. As a result of that, the weight of that object will be directed up downwards. to be directed downward. And I'll show that in a diagram. So let's say this is the mass. So its weight is directed downward. So this is the weight. So it has the weight is always downward, which is 20 Newton. That's it. So this mass is supported. So this mass is, let's say there's a string that is holding this, and then it's supported by two cords. Let's say they are strings, wire. So this is one of them. The other one is this. So these are the two chords, chord 1 and chord 2. And it says they make an angle of 30 degrees and 50 degrees with the vertical. So this is the vertical. Let me use red. This is my vertical line. This is vertical, and this is vertical. This is horizontal. So they make an angle of 30 degrees and 50 degrees with the vertical. Then we are asked to now calculate the tension. So the tension is on the cord. Should be on the cord, and this way. So we can see these are concurrent forces, all of them at this point. T1. Let's call the tension may not be equal, so let's call them T1 and T2. So we use that to calculate, to do what we need to do. Now we can draw the triangle of forces. Let's draw the triangle of forces. That's the first thing I'll guide you. Remember our rule, we draw them to be parallel to the line of action. So the force, so for the 20 Newton, this is for it. It is acting downward. 20 Newton, you can see this is vertical, so I'm drawing vertical. For the 20 Newton, for the T1, you can see, let me draw it. I'm drawing parallel to it. This is T1, drawing parallel, so this is T1. For T2, you can see this is T2. Yeah, you can see this T2. I'm drawing it also. You see, I formed a triangle. Then, having drawn the triangle of force, the next thing is the angle. Remember, we have angle. And for you to get the angle of this triangle, you just need to do simple things and draw your horizontal and vertical at the three vertices. If you are able to do this, then you start transferring from this. So let's go to what angle from here. T1 makes an angle of 31. This is T1. It's making an angle of 30 with the vertical. I see where I'm shading. That's T1. It's making an angle of 30 with the vertical. I come to this place. Where is T1? This is the vertical. Yes, so is this the angle? That's the 30. Yeah, 30 degree. So if it's 30 degree, this place is vertically opposite to alternate to that side. So here also 30 degree. So we've gotten one angle. So let's move to for T2. T2 is making an angle of 50 degree with the vertical. If I come to my T2, where's my vertical? This is vertical, I can see. It's making an angle of 50 degrees. So I can get the third one easily. And from we can also get it from here, but we've gotten two sides, so it's easier to get 50. Subtract the sum of this from 180. 50 plus 30 is 80. So this should be 80 minus 180 minus 80 is 100. So here is 100 degrees. So we've gotten three sides of our triangle. Having established that, we can now solve and use the cosine rule very well, or the sine rule, but preferably the sine rule is better in this case. So let's use the sine rule there. So the sine rule will take T2 and T2. What is this? Always, if you want to make it easy to not to get confusing, just draw your line to the and from the angle to the opposite side. You can see this 30 and T2 and 30. So T2 over sine 30. Let's go 20 and 100. You can see 20 and 100. So do 20 over sine 130. And then you can see T1 and 50. So let's do T1 over sine 50 degree. So I'm taking any two. For me to get T1, I'll take these two and solve. So let's take that two. 20 over sine 60 equals T1 over sine 50. So I can make T1 the subject formula. T1 equals to 20 times sine 50 over sine 60. So what do we have there? I use my calculator to get that. This is my calculator. So I'm punching the calculator now. 20 times sine 50, 20 times sine 50 divided by sine 60. What do I have? I have 17.69. So I have 17.69 Newton. That's the value of my T1. I can use these two to get my T2, and that is T2 over sine 30 plus 20 over sine 100. So you can see to the subject formula that 20 times sine 30 over sine 100. So using my calculator once again, that's what 20 times sine is sine 30 divided by sine 100 equals to 10.15. 10.15 minutes. So we've gotten this done. Any question? Yeah. Okay, so this is T1, T1. So I'll leave you to do this yourself and practice this yourself. So you can work on this to test your understanding. A picture of which coordinating is supported by a string shown below. Find the picture. Find the tension on the string at A and B if the strings are each inclined at 70 degrees to the vertical. They are inclined at 70 degrees to the vertical. So this is the diagram. We have box like this. The width of the picture is 4 Newton. The width of the picture is 4 Newton. So the angle this made with the vertical is 70 degrees, sorry, 70 degrees. This is 70 degrees. The angle this made with the vertical is also 70 degrees. So you have to get the tension. That means the tension on both strings are equal. That's why they are TT. So you have to find the tension. Note that this force here, if you are drawing the force diagram, which is vertical, so you can see them as concurrent forces. So just draw. Please, if we have three forces, T, T, and 1 Newton. So draw them.